We can start. So welcome to the seminar. Today's speaker is Adam Rançon, who is lecturer at the Laboratory of Physics of Lasers, Atoms and Molecules at the University of Lille in France. And he is currently on a short visit at the Institute of Physics in the group led by Dr. Ivan Balog. He was also a visiting researcher at the Institute of Physics in 2022 and 2023 in the same group led by Dr. Ivan Balog. He obtained his PhD thesis in physics in 2012 at the Sorbonne University and had two postdoctoral trainings, one at the University of Chicago from 2012 to 2014, and the other at the University of Lyon from 2014 to 2016. So today, he will talk about observation, quantum criticality, 4D in an ultra-cold-atom experiment. So the floor is yours.
Thank you. There's some typos in the title, but that's fine. So thank you for being here. It's always a pleasure to be here. As you said in the introduction, I've spent a year last year in Zagreb. It was great. I'm very pleased to be back for even if it's just for small visits, short visits, and especially since I've been working long hours with Ivan, but being far away from administrative duty and lecturing is like vacation, so it's great. Okay, so today I want to discuss this recent results we have in Lille. So I will present experimental results that have been obtained in the group by Rançon, with whom I'm collaborating for a few years now. And it's an ultracold experiment, ultracold-atom experiments where we've looked into quantum criticality in a four-dimensional system, or effectively four-dimensional system. That will be the point of the talk to explain how this is possible and why it's interesting in this case. So I'm a theorist, so I will present some experimental results. So you can, of course, ask me any question that you like, but I'm not sure I will be able to answer any questions that are too specific about the experiments itself. Okay, so the idea here is, of course, that you cannot really prove the physics of a four-dimensional system. Four dimensions are special dimensions, not counting time. And the way you could go around that is to use what people have been calling quantum simulators in the recent years. So, which is a weak version of quantum computer. So if you want, a quantum simulation is an analog quantum computer in the sense that you prepare a physical system and you hope that you control it good enough that it models some interesting physics, and then you run the experiment, and from that you get a result, and you pretend that this is a computation. So if you want, the idea is to have programmable and very well controlled experiments that model that do analog simulations of model Hamiltonians that you want to understand better. So an example, first example, I'll give some more afterwards, is imagine that you are able to very well control ions by trapping them in some potential. Then in some regime, the physics of those trapped ions is similar to the physics of a quantumizing model in a magnetic field, which is a problem that in some cases you know to solve pretty much exactly with for some Monte Carlo simulations. But if you're interested in the dynamics, then this is a very complicated out of equilibrium quantum many-body system that is very hard to solve on a classical computer. So you could hope that doing experiments would be a way to shed light on the physics of this kind of models, which are simple but yet hard to understand. So the idea is like that, shed light on very hard problems, for instance, ITC superconductivity, which we still don't quite yet understand theoretically, or out-of-equilibrium quantum many-body problems, or some more exotic physics, which like the kind I will discuss now, like higher dimensional systems. So to give some examples of quantum simulators, so people have been playing around with, for instance, trying to simulate a Fermi contact model with quantum dots or with ultracold-atoms, where here the hope is that if you control well enough the system and the temperature and everything, you can perform measurements on this kind of system and try to see a transition to ITC superconductivity or the equivalent, or at least find a way to understand what is the proper order parameter this kind of physics. I mean, yet people have yet to be able to do that in the relevant regime of temperatures. For instance, in ultracold-atoms, the prime is to go to a low enough temperature to be able to see this antiferromagnetic ordering and then superconductivity. Another possibility is to use like atoms to simulate quantum spins. So with that, you can engineer pretty much whatever Hamiltonian of quantum spins that you want with the external field, for instance. So these maps onto quantum Heisenberg models, quantum XY models, quantum Ising models, and you can put everything out of equilibrium in the lattice that you want with disorder, without disorder, and that makes also quite a complicated physics for theoretician, and maybe this kind of experiment can tell us something about it. And some other ways, for instance, try to simulate the physics of higher dimensional systems, what I was about. So here's an experiment done in Munich where they looked into the 4D quantum world physics with cold-atoms. So in my case, what I will discuss is the physics of Anderson disordered single particle quantum systems. So the Anderson physics, I will get back to what it is in a second. And we did that, my collaborators did that in their experiments, cold-atom experiments, to have pretty much a quantum simulator of this kind of physics. And with that, in the recent years, I mean, for quite some time, maybe like 15 years, they've been using this kind of quantum rotor model experiments that we described to probe the physics of the 3D Anderson transition, 2D Anderson localization, some more specific effects that you can have when you break times reversal symmetry, and so on. So that is the kind of quantum simulator I will discuss today. So first, reminder of what is the physics of Anderson localization. So the idea here is very simple. You imagine a 1D system, you have disorder, so this represents the disorder potential of the system, and you start with a wave packet which is centered at zero at the origin, and you let the wave packet expand. So what will happen that this wave packet will try to expand in this disordered potential. There will be scattering and back scattering in the random potential. So the wave will accumulate random phases, and you have scattering. And at some point, the wave cannot propagate anymore, and it's localized. So the width of the wave packet goes to constant, and if you look at the density profile, it is exponentially localized in this potential. So that's the basic physics of this very simple model. And in fact, this physics is very universal. You can see it in many systems. So for instance, classical waves, so in photonic lattices, with sound waves, with seismic waves, this has been explored, or with matter waves, so quantum systems, called atoms, electrons, or electrons is much harder to see because you have the effects of interactions, and which might make it difficult to access. But for instance, these experiments by the group of Alain Aspect 15 years ago, where they've seen this Anderson localization in a 1D system. The idea, so just to give slightly more background, if you think in terms of a tight bending model, you'd have random energies here for you. So psi is the wave function on the lattice, position I in, let's say, 3D or 2D, or whatever dimension you want on the lattice, square lattice, let's say. Then you have random energies, and then you have a hopping. And what you look at is different eigenstates of this random Hamiltonian, where the energies, random energies, are taken, for instance, from a uniform distribution. And what happens is the following. So here I'm not in 3D, let's say. What happens is that if the hopping is very small, then the states will be localized, as I have explained before. And if you look at the typical eigenfunction, you see that it's very well localized in the system. If the hopping is very large, or the disorder is weak, then you are in a delocalized or diffusive states where the eigenfunctions are spread over the whole system and you don't have localization. And in between, well, you have a quantum phase transition, you have a change of the eigenfunction. Oops, sorry. The change of the eigenfunctions, and you have a critical state, which is multifactorial. It has a lot of very interesting properties, and that's what I'm interested in. So critical properties at this transition. What's important in this kind of model, where you have So it's in real space, you have disorder on site and some hopping. That's this threshold at which you go from localized to critical state depend on the energy. So you have a mobility edge, which means that when you do experiments, this is hard because depending on the state of the, let's say, electrons and the energy of the electrons, some of them are localized, some of them are delocalized, which makes it hard to study it experimentally. So I'm a theorist, so I'll give some discussion about the theory behind that. I explain why it's very hard. In fact, we have learned a few years with Ivan trying to do some calculation on this kind of problem, and so yeah, that's still, let's say, still ongoing work. So the difficulty with this physics is that everything that you can see is at the level of the propagator of the diffusion, if you want. So it's sorry, the diffusion or the conductivity, which is a complicated thing to compute when you have disorder. And so they've been able to write a field theory for that. It's called supersymmetric nonlinear sigma model. It looks simple here, but in fact, it's a very complicated beast. And the important thing here, just for the discussion, that you have a diffusion coefficient here. So if you want a stiffness, if you think in terms of spins, and you have a field here, lambda, which depends on the energy of the wave function, which is a symmetry breaking field. So you can think of magnetic field in some kind of weird supersymmetric space, which breaks. So for an Ising model, it would be the external field, and this would be the interaction between the spins. And when you change this constant here, you have a critical value where you go from this localized to the localized states. But what makes it very, very difficult from a field theory point of view, that's the average value of this field Q here, which is kind of order parameter, if you wish. In fact, it's not an order parameter, it's not critical. It doesn't scale at the transition as we would have in a usual second-order phase transition. And so it's not a good order parameter, and that makes everything complicated. However, you can do some very simple scale dimensional analysis. And if you say, okay, my length is here, X is a length, then if you want to put everything together, because this Q doesn't have a dimension, then my frequency should scale like the inverse of the volume. This diffusion should go like this, and so time should go like L to the D. And this tells you that you have a scaling variable which should be space times T to the power -1 over D. So that's one prediction. And then if you assume that there's only one typical scale that is important in the physics of the transition, then you have only one scale, which is this localization length in the localized phase, and that will diverge at the transition, because at the transition states which were localized become delocalized. And they diverge with some exponents, mu, that we would like to measure or compute. If you put everything together, then you get this scaling law here that tells you that the diffusion coefficient should go to 0 with an exponent s, which is not independent from this mu, but obey this scaling law that has been first obtained by Wegner in the 80s or late 70s. Okay, so all of what I've discussed is quite generic about this Anderson transition. So what do we know about it? So in particular, what is the effect of dimension in this system? So here we just discussed the system with 10 reversal symmetry and without spin. So it's just the details for the experts. So what happens? So if you are in 1D and 2D, then what is known is that in this case, all states are localized. You don't have a transition. And in 2D, right, everything is localized, but with some exponential, everything goes exponential. 2D is a lower dimension of the system. And this physics has been observed like in 1D, on the localization has been observed in many systems, and 2D also. In 3D, you have a transition, as I said. And this has been observed also in cold-atoms or in electronic systems. Then you could ask, okay, what happens in higher dimensions? At first, it could be a nice question, because usually in high dimensions, phase transitions, they become a bit boring. They become mean fields, and there's nothing much to say. But in particular, in this kind of physics here, things are quite different. So first, in high people, like in the 80s, they found this self-consistent theory of Anderson transition. And what they found is, which looks like some kind of mean field calculation. And what they found is some critical exponents, some prediction for this critical exponent nu and this exponent s, finding that there should be a drastic change of the transition in dimension 4, as you would have, for instance, in the Ising model when you look at the ferromagnetic parametric transition. And that would suggest that you have an upper critical dimension, which is 4. However, numerics says otherwise. Now you have very strong numerical studies that show that this, at least up to dimension 6, this exponent nu is more than 1/2. So it's not consistent. The self-consistent theory appears not to be valid. And in fact, there have been some arguments that this upper critical dimension of the system, so the dimension at which the physics become midfield, should be infinite. And by some mapping onto a better lattice that I don't want to get into. What is important to stress is that there's no quantitative results beyond 2D and what people call the 2 + epsilon expansion. So pretty much we have no idea how to compute, like from the theoretical point of view, the critical exponent nu in dimension 3. And there's numerics, but no calculation, no laboratory calculation, and same thing for all the other dimensions above. Okay, so that was done with the theory part, pretty much. So the idea that we had was to try to look into this Anderson transition in 4 dimensions using some kind of quantum simulator to try to see if we could find this non-trivial physics in dimension 4 for this transition. So to do that, we use this quantum key product. So it's a model, but it can be very well realized experimentally. And so the model is very simple. It's given here, so it's a one-particle problem, so you can forget about interactions between the particles. You have kinetic energy term, and you have potential term that depends on time. And here I'm just choosing units such that my position and momentum are units such that, yeah, h bar is replaced by this k bar. K bar is something that you can change experimentally quite easily, for instance, by changing the periodicity of the kicks or some other quantities. And what is okay? So what's the physics of this model? So imagine you have your cloud of atoms, they are non-interacting, and at t = 0, you kick it. So you apply a cosine potential that you can realize with a standing wave with a laser, with a carefully chosen frequency of the laser. So you apply a kick. So what does a kick do for particles? If you change their momenta, you apply a force, you change the momenta. So if you think in terms of momentum space, then you're hopping in momentum space, right? You have a wave of some momentum, then you hop by applying force, and then you let the cloud expand. And so you have a free propagation. So each momentum state will propagate. So you just accumulate the phase. And this phase, if you choose all the parameters carefully, in particular this value of k bar, then this phase is pretty much random. So you accumulate a random phase, and then you kick again. So you mix every momentum state, and then you expand, accumulate a random phase. And this looks like this scattering of a wave in a random potential. And in fact, this is exactly the case. If you look at the average kinetic energy of the system, so these are simulations, but you look at the kinetic energy of the system as a function of time, you see that at first it grows with a number of kicks, and then it saturates. Whereas if you look at the momentum distribution, so the wave function in momentum space, this is in semi-log scale, you see that it's exponentially localized, like straight lines here. And this looks pretty much like Anderson localization, but in momentum space. And in fact, it's exactly that. You have a kind of mapping between the physics of this model here and the physics of this Anderson localization that I've said before. Yeah.
Is this truly random or just very weakly correlated, like in the quasi-periodic rules?
It's I think it's less correlated than in. So you have small correlations. I think it's not onto Cauchy distribution, something like that of the phase. In the limits where, I mean, if you control the limits.
Because even in the random localization has been proven, let's say, quasi-periodic, where in many cases it's only distinguishable.
Yeah, so I think here you can show that the phase is distributed like a tangent of something, that tangent of the momentum square And this oscillates so fast that it's pretty much the same thing as a Cauchy distribution. And then for the Cauchy distribution, you can prove that they're on the same localization. But here, I mean, all the numerics, everything that you can think of is there's no problem in that context. And then the hopping is not short, it's not nearest neighbors, it's longer range, but it's not long range, but it's on, you can hop to many neighbors with an exponentially decaying probability. And it also doesn't change the physics. The physics of Anderson is universal, so we expect that everything should work fine. But for instance, contrary to the case where you have quasi-random potential, where there you have a mobility edge, here you don't have a mobility edge in one instance. Okay, so that's so this dynamical localization, it has been observed 30 years ago now in a group of regions. But you can do more than just looking at this. So this looks like Anderson localization in one dimension, right? You apply kicks along the x direction, you forget about the other degrees of freedom, and you have localization in momentum space along the x direction. But what you can do is create synthetic dimensions, and that will be the trick for the experiments. And the idea is very simple. You start by modulating the amplitude of the, or in fact, the phase of the potential here. So this K now depends on time. So it's a quasi-periodic, quasi-periodic variation. So you have 3 frequencies here. We get 2, 3, and 4, which are all multiple of each other, and with 2 times. So you have something that's really spreading periodicity. And then when you play the kicks, then you just choose one value depending on where you are in this sequence. And now what you do is this very simple trick. You just rewrite the dynamics of this Hamiltonian here with a time-dependent kick. That way, where you introduce new coordinates, which are synthetic coordinates that evolve like this time, like linearly, and you introduce this new momenta, but also obey rotation relation with this x's. And this, the physics of this Hamiltonian here is exactly the physics of that Hamiltonian. If you choose a good initial condition, you can trust me on that. But what it means that now you see that I still have one real space coordinate, which is p or x, and then I have synthesized 3 new, or I could do that with more, right? To have the physics of an effectively higher dimensional system. In fact, if you look at what are the flow-Canadian state of this Hamiltonian here, which is not periodic, this one is not periodic, but this one is, and you go through the whole thing, what you find is, I mean, this is pretty much not the mapping I was talking about. You find that you have a pseudo disorder that goes like momenta like that, and you have the hopping, which is very transformed. That thing, who cares? Just trust me that you, in the end, have the mapping onto a weird 4-dimensional system on a lattice with disorder. So what do we expect from this physics? So you take this, here I'm showing the phase diagram that cannot think numerically, as a function of 2 parameters. K is the kick strength here, and epsilon is the mixing with the other dimension. So here, if epsilon is 0, I'm back to my original problem, which is 0, which is 1-dimensional. So in that case, everything, every state is localized, and then I increase. If I increase epsilon, then I'm adding more dimensions in my system. So here is the phase diagram. In blue are the localized states. In red are the delocalized state, and you see that if you go through like that, for instance, diagonally, you find that there's a transition from this localized state where the wave function is like that to a delocalized state where the wave function is Gaussian and the width increase in time. So here, if you look at this here, so you look at the width of the wave function, it goes like d times t, where d is the diffusion coefficient. If you are in this localized state, then the wave function is localized exponentially with a localization length, which you can also extract from the width. Here I call it p log because it's localization length in momentum space. And this localization length diverges when I get close to the critical point, and close to this transition line. With so delta k is the distance to this transition with an exponent mu, and here it's the other way around. If I go from the delocalized phase to the localized phase, by approaching this point, then the coefficient diffusion goes to 0 because at the position I'm no longer diffusing. And so this coefficient goes to 0 with the distance to the core of S, where S is this critical exponent I discussed before. Okay. So now, in the end, to get back to the experiment, what we will be able to do is to measure the momentum distribution of the atom. So we take time-of-flight photos of the atoms after your Kick sequence, and you look at what is the momentum distribution. And so we need to understand what we should expect to see. So from the scaling hypothesis I've discussed before, you can assume that the phi of t and p is a momentum distribution at time t for given momentum, the probability to have momentum p at time t. And we expect that it takes this kind of scaling form. So you have t to some power, function of p times t, and then distance to the critical point with some other exponent gamma. And if you want, you can also write that the same way for the width of the wave packet, the average of p squared. And so if you play around and you want consistency between the localized and delocalized space, you can relate this exponent alpha, beta, and gamma to this exponent mu and s that we had before, assuming that we don't know the relation between s and mu. And if you know it, if you assume Wegner scaling law, then you find that there's only one exponent that is independent, mu, and it also involves the dimension of the system. So in the end, what we will try to measure is this s and this mu and verify that it is consistent. So that's the one photo about the experiments, because I don't know how it works. But pretty much it's a potassium experiments that we have access to a Lorentz condensate. Now these days, even though here to reduce the effect of interactions, what we do is that we keep this, what they do is they keep the atoms relatively hot around 1 microkelvin. Here are the parameters that are used in the experiments. And so what you have is a vacuum chamber here, the atoms are somewhere here, there's a camera, there's a lot of lasers to do stuff and keep the atoms and plot them and whatnot. And okay, so it's complicated. But at the end of the day, what we get is this kind of data. Here you see absorption image of the cloud after some number of ticks. So T is the number of ticks here. The darker the figure, the color means that you have more atoms. And here is the direction on which we apply the kicks. So you see that as we improve, so as we kick more and more, the system, the atom, so you can forget everything that happens along that direction, but as you kick more and more, you see that the atomic cloud gets elongated in this direction. And in fact, from this photo, we can extract directly the momentum distribution of the atoms. But to analyze everything, what we need to know is we need to know where is the critical point. So, right, when we change the kick strength, if I go back to my slide here, to analyze everything, we need to know the distance to the critical point that we are at. So we need to find what is this critical value Kc here. And we need to do that in the experiment. So the way to do it is to find a combination of observables that behave nicely. So if you think in terms of Binder parameters, if you do Monte-Carlo simulations, that will be the idea. So we create this quantity here, so it's momentum distribution at 0 squared times the width of the momentum distribution. And this scales nicely. And so what you have here is data, so it's data taken from the experiments, where you can see that if the kick strength is not, yes, okay, if the kick strength is small, this number here after a short time like grows. If you kick too hard, it decays here, and in the beta it goes flat. And this is how we find the critical point. So we look where this thing here, this quantity here, doesn't depend on time. So when delta is 0, then P of 0 is just constant, and that tells you that you are at the critical point. So if you do that on the triple value of the kick strength, what we find is that this slope here goes to 0, and that way we find what is the critical point right from the data, the numerical experimental data. And then what we want is to find these critical exponents S and mu from the same thing, from the experimental data. So here, what I show is this p-squared, so the average kinetic energy of the atoms, for different value of the kick strength here, and the different bonds are different types. So as you can see, and the darker the bonds, the later in time here. So if you think at a given k, you look at as time increases, then the widths increase and then stops here. Whereas if you're at very large k, when you are in the delocalized phase, you see that this width always increases. And at a critical point, it should do something in between. And so the idea is to take the data, and if we have a scaling law like this, then there's a way to rescale the data and rescale so the x-axis and the x-axis and the y-axis, such that everything collapses onto a single curve. So this is what we try to optimize. So we optimize alpha and gamma, if you want to optimize the exponent mu and s, to find the optimal way of collapsing the data. So as you can see, it works quite well. And from this, we extract the critical exponents. So here, the different dots are different. So we do some kind of bootstrapping to find what is the critical exponent. But in the end, experimentally, what we find is these values here. So it's this 40 Anderson-Lopez transition. We find it with a mu, which is about 1.1, let's say, and it's exponent s, which is about 2.2. And we try in good agreement with the best numerical simulations in 4D. And you see that we are very far away from this like midfield-like or self-consistent theory that predicts an equivalent 1/2 for mu and 1 for s, and we are very far away from that, which is good because we expect that to be wrong. That it's I guess the first confirmation of that. And we also see that this Wegner scaling law is well verified. So we don't assume it; we just find it from the expression. But we can go beyond that. So here we have done that for one observable, but in fact we can go even better. What we can look at this momentum distribution, and so we expect that it should take a form like that. So it has dependence on time, and then it's a function of two parameters. So it's a function, a priori it's a function of three parameters: time, momentum, and the distance to the critical point. And if we scale everything correctly, it should be a function of these two variables, p times this time to the power 1/d, and the distance to the critical point with this time to this forward here. In particular, if you are right at the critical point, so delta is 0, then you should expect scale invariance, so the function of p and t, which is just a function of p times t to the power -1/d. And this is indeed what we find in the experiments. So here you can see this momentum distribution that has been measured. So it's the same data that I showed with the photo. I showed the photo of the cloud. From this, you can extract these momentum distributions for different times. And you see that if we rescale, if you rescale momenta by the correct power of the time and momentum distribution by the correct power of the time here, we find that everything falls onto one single curve, which shows that we indeed have scale invariance. But we can do even better. It's that we can also have so what we expect that this momentum distribution obeys two parameter scaling laws. It depends on function of two parameters. And indeed, what we see that it works. So if we keep, what we do is we do multiple experiments at different value of the kick strength and at different time, and we choose time and kick strength such that we keep these numbers here constant. So for instance, here about 2.7, -2.7. So in the localized rate, so all of these curves are in the localized phase, but close enough to the critical point, such that if we rescale everything, keeping this constant, everything falls into one single line, which looks like localized-ish with an exponential decay. And we can do that, of course, for different values of this parameter here. You see again, it's very nice collapse, or on the delocalized state, where then the scaling function looks more like a Gaussian-ish state. And then you can take all the data, so data from a lot of different cases at different times, and you can collapse that onto one single two variable function, so one surface here. So you can reconstruct the full two parameter scaling functions as the distance to the critical point we scale this time and the momenta we scale this time. And you see that this nice smooth transition from a localized wave function to a Gaussian one with a critical wave function in the middle. Okay, I think with that I'm pretty much done. So what I've shown that we have been able to observe this Anderson transition in 4 dimensions using this quantum simulator. We find like we've been able to measure this, to extract these critical exponents, which is I must spread that. Usually in experiments, it's very hard to extract critical exponents. This here is manageable because this quantum key proton is very nice to study the Anderson transition because we don't have a mobility edge. We are able to do very precise measurements, and then the data analysis for the hard parts here to be able to find the best way to extract these exponents. Okay, so we found that was expected from an experimental point of view, but it's an experimental proof that in 4D this Anderson transition is not meaningful. And okay, and I think this last figure that I showed you is a very, very nice way of reconstructing the 2 parameter scaling function, which is, I think, also something that is really very hard to do if you're not doing numerics. Yeah, so then what would be some outlooks? So one thing I would like us to do is to check this Wegner scaling. So here we have checked one that I found, one value of dimension. We have this Wegner scaling law that is obeyed, that from S is related to mu. But I think it'd be nice to show that it's as a function of dimensions, it's indeed obeyed. So it's really a scaling relation. Yeah. And of course, I've been interested for many years in the effect of interactions on this transition and how interactions and this dynamical localization could go together and what it will imply. And hopefully, this is the kind of experiment that we will do soon indeed with my colleagues. And with that, thank you for your attention.
Are there any questions?
Yeah. And actually, one is can you add additional dimension? I didn't really understand the trick, so it's not clear. The second one is that if you have any way to probe also the inverse participation ratio to understand the different times.
So for the first solution, yes, you can in principle change the dimensions. It's very easy because add more frequencies in these values. That's how they did 2D, 3D, 4D. It was just adding one. I think the reason why they didn't do it is because they thought it would be hard to see anything. And I mean, then I just convinced experimentalists we should try and work with it. The difficulty is as we kick more and more. So you see with the scaling law, as you keep, you can see here, as you keep more and more, you see that as you increase d, this thing gets smaller and smaller, which means that the dynamics that you see is it looks like very slow. So it gets harder to extract anything. So I think we will try 5D to test this Wegner scaling law, but probably then it gets just hard because here, of course, I gloss over a lot of details that in experiments you cannot do a billion of ticks because you have coherence in the system and stuff like that. So here I think they do about between 500 and 1,000 ticks, but we cannot do much more. And so you see, even if you take like 1,000 here and you forward 150, that's actually more. So probably dimension 10 would be very, very hard to do. So in principle, that's the goal. And for the multifactoriality is something we would like to see how to probe. Probably it's also very hard for the same kind of reasons. So one work I know on multifactoriality on this specific model. What you can look at is how this momentum distribution at criticality, where I have it here. This thing here. At long times, you should have a peak that emerges, which is related to multifactoriality. And the problem is that it's hard to see, and you see here, this is a bit broadened because the initial distribution of the atoms, the distribution of the atoms is not perfect DR delta, you have a bit, so you have to convolute everything. And so probably here it will disappear. And for the inverse participation ratio, I don't know, I don't really know how to measure it. You know, we have access to the momentum distribution of the atoms, and that's pretty much it right now. So, but that's a, and if you have ideas, I would be very happy to look into that.
So you mentioned that the exponents you get go beyond the mean field theory. So what do you mean by mean field theory?
So there's no mean field theory, but there's the closest thing that could look like a mean field theory is self-consistent theory here. I haven't discussed it, but it's this thing is you, from a theory point of view, you write an equation for the diffusion coefficients, and you write it self-consistently, and you solve that, and that's the closest to a simple theory that you have in this point of view. And this thing predicts that you have an vertical dimension, but it's wrong. But yeah, there are no true mean field theory for this. That's right.
Where are the experiments done?
Yeah.
Impressive. This experiment.
Yeah, it looks very scary. I mean, I never go to the basement to see it because it's really.
And really, there is a problem with time, especially with increased dimension, because we are losing the package, obviously. But how difficult this model would be to include interaction, this experimental setup, and stick with one dimension.
So you mean doing the theory? Or the
theory? No, but the experiment.
So the experiments. Yeah, so the idea, so there's, I mean, then it's another kind of form, because if you think in terms of a 1D system that you keep with interactions, then depends what we mean by 1D, because you see, if you don't confine the system in the other directions, then your cloud is able to expand, right? And so the interactions is 3D, even though most of the dynamics is 1D. This, to my knowledge, I mean, there's been some experiments on that. What people see is delocalization transition. So pretty much you don't have localization at all.
Yeah, I understand. You can't actually do 1D.
So the other idea is to confine the system to new lattices. And so some people, that's really what we want to do, because I've done a lot of calculation on very specific case of 1D confinements where you have a linear model and you have some kicks, and then the dynamics is quite rich. And we want to do that. It's a matter of putting more lasers to have a lattice, very strong lattice in 2 directions. So you have kicks, and then and then the brand that you have a trap, and the trap can also lead to delocalization or something like delocalization. So there have been experiments in the US where people have this kind of setup. They have 1D gases that they kick in a very weak interaction regime, and they see the localization, but we think it's probably due to the trap effects. And so if you don't want that, you need to put an unstrap, and it gets very messy.
More questions? Any questions from the online audience, maybe? Okay, in that case, let's thank the speaker one more time.